Good morning, ladies and gentlemen. My name is Ricardo Batista, and I will present you the paper entitled Fatigue Crack Growth on a Modified CT Specimen Using Artificial Neural Networks. I'll start by a brief introduction to the problem, followed by the finite element method and artificial intelligence methodologies used. Then we will see our obtained results and, of course, the conclusions. So our main problem is fatigue crack propagation analysis. This is a very complex problem that requires one to determine the crack front position and crack shape along a given number of cycles, and we can do this experimentally or numerically. Of course, if we have a small geometrical modification on our component, our specimen dimension, or using different materials, then basically we have to repeat the whole process. In the case of the experimental approach, we have to manufacture a new specimen, perform the test, measure the crack location, and obtain the crack propagation law. Numerically, we also have to create a new model with different material properties or dimensions using different crack propagation criteria, and then the new finite element analysis gives us the crack propagation problem solution. But the problem remains. Each time we change one initial variable to the problem, then we need to repeat the experimental or the numerical approach. In this case, we based our problem on numerical results from the crack propagation on a CT specimen with a hole, but this hole can change dimension, positioning, and also the initial crack length can be different. We solve this problem using a finite element analysis approach, a numerical approach. We establish the initial conditions, then we create the model and define the material model, use the finite element solver to calculate the fracture mechanic parameters, and calculate the new crack length and direction, update the model, and start again. In this case, we are using the vector crack tip displacement criteria that considers the crack opening on the normal and the shear mode directions to calculate the crack propagating direction, and we use this direction to calculate the new crack position and the fatigue life to update the model. But this is a very time-consuming and resource-consuming problem. So we thought about a new approach to the problem, and that approach includes to use artificial intelligence to train a neural network based on our previous results to predict the crack propagating direction, update the model, and repeat the process using the trained network. And instead of a complex numerical problem that takes time to solve, in this case, artificial intelligence allows us to obtain the results instantaneously. Our artificially intelligence approach used a neural network, in this case a feed-forward neural network, with one hidden layer with 5 neurons in order to predict 3 outputs from 5 different inputs. Our inputs were the whole dimension or radius, the whole x and y position, the initial crack length, and then the crack increase along a given iteration. The outputs were the horizontal and vertical crack increment, and of course the number of cycles. We used 28 finite element simulations with 1,120 training points. The value of a given neuron on a given hidden layer is actually a linear combination of the values from the previous neuron layer with a bias added, and these values are further mapped to a -1 to 1 domain through an activation function. This activation function can be used with a hyperbolic tangent sigmoid function or a simple linear transfer function, and both of them are present on the neural network. The hyperbolic tangent sigmoid function is used between the input and the hidden layer, and the linear between the hidden and the output layer. It's also very important to guarantee that both the inputs and the outputs are normalized. And this is important in order to guarantee that the backpropagation training algorithm updates all the weights and bias throughout the neural network, and not only the ones inflated by a high value of the input or output variables. Finally, training the network is to minimize the difference between the predicted outputs and the expected values. And this is done by changing the weights and bias in order to minimize the loss function, which can be the mean square error measurement, for instance. In order to minimize these differences, the direction in which each weight and bias is updated should be calculated by the derivatives of the loss function in respect to each weight and bias, and this can be done by the Bayesian regularization backpropagation algorithm. Of course, the performance depends on the initial estimation of the weights and bias, and in order to choose the best network possible, we perform several trainings with different initial sets of weight and biases, and only retain the best performance network. As we can see, by using a trained neural network using 28 finite element simulations and a 2D model, we can see that the fatigue crack propagation path and also the fatigue crack propagation lives can be accurately predicted using different initial conditions, and these conditions were the size and the position of the hole, and also the initial crack length. We were also able to divide the training data into smaller subsets, like using only 13 simulations to predict crack propagation on a problem where only the position of the hole is changed, or using a different subset of simulations to predict crack propagation with 5 inputs, so the hole position, the hole dimension, and the crack initial length, in order to accurately predict fatigue crack propagation. So you can use a smaller subset in order to predict crack propagation. Extrapolation of results is still not recommended. Okay, so as a conclusion, we can say that a neural network was used to accurately predict fatigue crack growth on a modified CT specimen. Mixed mode crack propagation was introduced by adding a hole to the specimen, but the position and the size of this hole and also the initial crack length can be changed. Using data collected from 28 simulations, the neural network was trained and was able to predict both crack paths and specimen fatigue life using 5 different inputs. Input and output normalization is a crucial step for neural network training and accurate predictions, and is a fundamental step for obtaining accurate results. I hope you have enjoyed our presentation. Thank you very much.